If we now look at analyzing raster data, this is a very brief look at just some methods of analyzing raster data. In another lecture later on, we will go into more detail about some of these analyses, but this is what we're capable of doing. This is just some general outlines of what we can do, some of the basic things, why you might want data to be in a raster format rather than a vector format. So the first category we can look at very, very quickly here is the kernel or neighborhood operation. This is where we look at a collection of cells or pixels together within a particular area. Usually these are statistical operations. There are a couple of other things that we can do. We can look for edges and so on and so forth using, say, Sobel operations. But what is a kernel then, or a neighborhood? Well, we define a neighborhood as being this movable square that you just saw fly in there, that moves over the raster, and for all of the cells within it, it performs a calculation and then puts a new value into the center cell. So we start off with this original raster in the background here. We move in with our neighborhood, which is this deeper, darker, thicker line here, and we collect all the data from within that neighborhood, perform some operation on it, and then replace the center cell in the original, the raster behind, with that new value. And then we move this on one row or one column and perform the action again and replace the center cell again. It's usually they are 3 by 3 or 5 by 5 or some multiple of an odd number in order to create a center pixel in which the data will go. Let's just look at this. So if we want to take the average, which is quite common, we're going to take the average value for all of these. So what do we want to do? Well, our kernel will look like this. What does that mean? Well, each of these are going to be applied to each of these in order. So that one is applied to that one is applied to that one, that is applied to that one, cell by cell, for this new value, this one new value that we're going to create there. So we are performing this calculation. We are calculating the average of all of these. So each of these contributes with 1/9. There are 9 cells, so they all contribute with 1/9 of the value. So we just multiply, looking at this, we'll look at this first column here because it gets messy if I put arrows in everywhere. But the first column, we've taken this 5 from here, and we've taken the 1/9 from there. We multiply them together. We've taken that 6 from there, and the 1/9 from there, and we multiply them together, and likewise, and we carry on across all 3 columns, so that we end up with this sum of, in this case, 4.2, which we then put in to our new raster. So this has been converted into that. So we took the average across for each movement of this kernel. We went from one position to another position, moving all over the kernel, and at each step we calculated a new mean, and that new mean is put into the center cell for our new raster. Now there are some questions about this when we get to the edges. What happens at the edges? That we'll take up in a later lecture. But for now, we've just performed a statistical operation on this neighborhood, on this kernel here, this neighborhood of cells. We calculated the average and replaced the center cell with the average value. Why would you want to do this? It can show us trends across a surface, for example. That's one reason for doing it. So that value gets put in there. That's what that arrow is showing us. Or, alternatively, instead of a neighborhood analysis, we might want to do something. We're now looking at class data. So the previous slide, that was more for continuous data. You wouldn't really want to take the average of classes because, well, what's the average of say, water and forest? Very wet forest, perhaps. So class data tends not to be averaged, hopefully. But now when we're talking about discrete data, or indeed with continuous data, we can do something called masking. And I'm going to exemplify masking now with this discrete data to show what we can do. So we have a soil map here. So each class of soil in this simple map here is represented by an integer value. And so class 3 is clay, and class 5 is sand, and there are other classes around for different types of soil. And then we can perform something called a reclass on that, where we just say, well, everything that isn't clay gets a 0. Whatever it is, I don't care, it gets a 0. But everything that is clay becomes 1. That creates our mask. So everything that is clay has become 1, and everything that isn't clay, regardless of what it is, in this case they're all 5s, but regardless of what it is, they become a 0. So that's our mask. And what's so great about this mask? Well, 1 times something leaves that something unchanged. 0 times something is 0, always 0. That's quite handy, because now we can take this mask and we can go to our land use map. Now these integers represent some form of land use, so woodland, pasture, arable, or built up in this case. And we can then take this cell by cell, so we multiply these together, that cell with that cell, that with that, over like this. We mask out. Where we have a 1, the data is unchanged. Where we have a 0, it gets zeroed out. So we mask out everything that we're not interested in. And we end up with this map of how clay soils are being used in our little map area here. And we can use that information to inform a decision, say. So how are our clay soils being used? Well, 2 of them are being used as woodland, 2 of them are being used as pasture, 2 of them are being used as arable, which is perhaps one of the better uses of them, and 1 of them is being used as built up, which is a complete waste of a clay soil. We can perform other operations. We just saw a reclass there where we took everything that was not clay and we turned it into a 0, and everything that was clay got turned into a 1. We don't have to stick to such a simple classification. We can actually inform ourselves more. We can decide to take continuous data and classify it into discrete data. We can have a range of values and say anything that is between, in this case, 150 and 159, well, that's class 1. What that class might mean, we might have some specific, these might be some form of elevation, or it might be abundance of some chemical or some grain that we're after, and we can say that, well, okay, anything that is between these values is class 1, between these values is class 2, and so on. This then informs us as to some other quality. It simplifies the data. We no longer have to store all of this extra data, because if we're not terribly interested in the exact values, we just want to know roughly how good something is, then these classes are perhaps just as good. And it turns out that this is a fairly simple translation, but we've gone from a potentially interval or even a ratio scale to an ordinal scale, really, here in this case. It's perhaps you could argue for this being still an interval scale, but that's not terribly straightforward to argue. But regardless, what we have is a reclass of data. The simplification, we can reduce the amount of data we need to store, but also we've perhaps informed ourselves a little more. We've made a decision about what something is. Is it good enough? Or what particular qualities can we associate with these numbers? Becomes more evident when we class it, perhaps. So it's a common enough function to use. But we can also do this classification of pixels when we're looking at remote sensing data. We can take the colors and look at the colors and say, well, this color represents one class or another. For instance, we can look at this and we can say, well, these colors, and this is where we get to a little bit of a lie here, really, which we'll get to in the remote sensing lecture. These colors, which you can see there's more than one color there, that represents forest. Well, this is obviously scrubby forest or new cut forest, new growth forest. Here we have some sort of grassland. We're just looking at the colors and we can see the colors change. Oh, look at those colors, completely different. We can take the values for stored in these 0 to 255 color bands that we've spoken about previously and say, well, we can class our data by the values that we find in there. And that's the basis of remote sensing from these raster images. How you do it is another matter. That's going to be taken up in another lecture. But once we've done this reclass, we can also reclass classed data. We've gone from one thing, but maybe we don't actually need to know the difference between the conifer and the broadleaf and the mixed and the clear cut. If all we're interested in is where do we have forest of some form, we'll class those all together. So we do a reclass into a sort of parent class, as it were. All of these belong to this woodland class. 2 to 5, all of these are all woodland. Once we've done that reclass, we're stuck. There's no way back. We can't pick apart class number 1 and say, well, class number 1, we know that it came from one of these maybe, but there's no way back. So when we do this sort of reclassing, we have to be careful that we then are stuck with what we've done. We can always go back to the original data, obviously, as long as we haven't destroyed that, that's still there. But in the new reclassed data, there's no way back. It has a lower resolution, we can say. Not spatial resolution, but a lower resolution in terms of the information that's stored there. So we have to be careful with doing that. But it's perfectly doable and it's perfectly legitimate to do so if it satisfies the needs that we have for the data set.